It was a very boring physics class. All I could do was count the seconds. Tick, 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 and then the bug. I got out my pencil. It walked. I marked its location every 2 seconds. Tick, tick, mark, mark. It slowed down. Then it sped up, and then it was gone. But a record of its motion remained. So I took out a ruler and measured some locations, 11 of them, for this 20-second trip. But that was just the beginning. I put the data into a table and then sketched a quick graph, slowing down at the beginning, speeding up at the end, moving in the same positive direction for the full 20 seconds. And that was a good thing, too, because if the bug had turned around, then the dots would have gotten confused. But these dots, they can tell us average velocity, displacement divided by time. The math isn't too bad. Look, here we have a constant velocity, values to put into the table, change in position divided by time, and I call this the speed at 3 seconds. Really, it's the bug's average speed between 2 and 4 seconds. And that isn't something I directly measured, but it is something I can graph. Technically, this is the graph. The red line segments each have a constant slope, and then on the right we have funny velocity plateaus. And fun fact, this is what the animation really showed. I did it in PowerPoint, and this is that. But it isn't very realistic for a living bug. The velocity probably should look more like this. Always positive, always moving left to right, but slowing down, constant, and speeding up. Looking at velocity, the difference between the first model and the improved model is easy to see. The difference is also present when you look at the position versus time graph. Straight lines become curves. Zoom in and see the straight lines on the left and the curves on the right. See the difference? Great! Let's take our data and our models to answer 2 questions. When is the bug's displacement 7 centimeters? And where is the bug after 17 seconds? First question first. Looking at the data, we see that the answer is between 2 and 4 seconds, but the data is limited. Looking at the graph, we'll find our answer here. But our first model misses the mark. And that's because we'll start by assuming that the bug has a constant velocity for the entire 20 seconds. It didn't, but if it did, then we could use the bug's average velocity to answer our question. And with a constant speed of 1.21 centimeters per second, the bug would have gone 7 centimeters in 5.8 seconds. It's a first answer, but not a good answer. The bug was moving faster at the start, so it would get to 7 centimeters in less time. With this model, we will focus on the second line segment and use the equation delta x equals v delta t. Nothing too scary here. We already found the average velocity in this segment will be 1.85 centimeters per second. We also know that the bug was at 5.5 centimeters when time equals 2 seconds. Therefore, the bug is at 7 centimeters at a time of 2.8 seconds, which looks good on our graph and fits nicely on our answer sheet. But this model can also be improved. Velocities change, and that means acceleration. More values to calculate and to fill into the sheet. Notice that the acceleration is negative. The bug is slowing down. And this is not necessarily the acceleration exactly at 2 seconds. It's the average acceleration from 1 to 3 seconds. And it might not even be exactly that. But if the velocity versus time graph looks like this, with straight line segments, then the acceleration graph should look like this. And I don't like it. Not just because we traded one funny-looking wedding cake for another, but also because that's 1, 2, 3, 4, 5 different accelerations, and that's too many. Let's simplify. That's not so great. This one I like. I like this one better. And because the acceleration is constant in our model, the 3 kinematic equations will work, so keep those ready. And write out an equation for the first 6 seconds of the bug's motion. We already found out what the acceleration needs to be here, and what its final velocity after 6 seconds needs to be also. So we can calculate the initial velocity. Very good. Especially if your next step is to use this kinematic equation to find the bug's velocity when displacement is 7 centimeters. That's all you'll need to know in order to find out the time it takes the bug to go those 7 centimeters. 2.6 seconds. A better model. Another answer. And if all that made your head spin, consider writing it out as a word problem. Nothing too special in this type of word problem except one thing. It's all a lie. We never measured that acceleration or saw it moving at this speed at that time. That last one is a data point we specifically invented in order to simplify the picture. All we really saw for ourselves or were able to measure for ourselves were dots, these dots on that page. And we built this model with these kinematic equations. Good thing we found the initial velocity. But these equations for position and velocity only hold for the first 6 seconds. In the next segment, the velocity is constant. Where did that 11.4 come from? Here. We want the two segments to give us the same position and speed after 6 seconds. The third line segment, acceleration is positive here, speeding up. And it's the same story. Kinematic equations, constants to make sure that our values line up. It's very nice. Take the first equation, testing out our measurements, and they don't match. They don't match here either. Well, why not? Well, why should they? I built my model to do a thing, to get from position 0 to a speed of 0.55 centimeters per second in a time of 6 seconds with this given acceleration. That's what I did, and it does it. If you want your model to, match the data, take these points, put them in a spreadsheet, and do a curve fit. Here's the equation it will give you. Very similar to our earlier equation, the only difference is the initial velocity drops from 3.25 to 3.20 centimeters per second. And with that change, the data does fit much better. But notice what doesn't fit. The two segments no longer agree with one another on what the speed is at 6 seconds. Internal consistency is sacrificed on behalf of correspondence with reality. Or something. But with this new equation, we can find again, and for the last time, how much time it takes to get to 7 centimeters. And if it seemed like we were solving the equation in a roundabout manner earlier, it was in order to avoid using the quadratic equation. Two solutions, but one is outside our limits. The other goes in the trophy case. 1 question down, 2 to go. Where is the bug after 17 seconds? There it is on the graph. Here it is zoomed in. The answer will be somewhere around 17.5 centimeters. Our first model, the one with that single constant velocity, will give us an overestimate. And there it is, 20.6 centimeters. Write it down and go back for a better solution using a line segment drawn with this data. Just like before, we know the average speed. We also know that the bug was at 16.6 centimeters at a time of 16 seconds. Using that, we can find the displacement at 17 seconds. It is 17.9 centimeters. That's definitely better. But now we move from constant velocity to acceleration with these equations, specifically the third one. And let's remember where it came from. We demanded that this be the acceleration, and that this be the velocity at 16 seconds. And what about the 16.9? Well, that was the displacement given by the second segment of the model at a time of 16 seconds. And that unfortunately did not match up with the data, which is, if you think about it, bad. Anyway, there's the equation. Plug in time equals 17 and get an answer of 17.8 centimeters. Add that to the list. As promised earlier, a curve is different from a straight line. But let's test the equation at 16, 18, and 20 seconds against the data. Not great. So again, we take the data to the spreadsheet, do a curve fit, find the equation. It looks like this, which is pretty different from what we had earlier. But then you expand and simplify the earlier equation so they look pretty close after all. The only thing left to do now is plug in a time of 17 seconds. Nice. But can we go one step further? Look again at that acceleration graph. Plateaus, a wedding cake. What about this? Can we do that? Well, if we did, we'd have to abandon those kinematic equations, but we'll take a look at it in part 2.